Hello students, today we're going to be looking over motion and talking about how to describe and measure motion. So distance and displacement is going to be kind of the key thing for today's notes. This is in chapter 10 if you're following along in your book. So first, measuring motion. Motion is described as a change in position. But in order to describe something in motion, we need to have a reference point. So each individual that's describing an object will have a different reference point, or possibly could have a different reference point. If you are in a car moving, you are going to describe things outside of the car differently than if you were standing on the side of the road describing those same objects. So if you're in a car and you're in motion, the car is moving, then you're describing things outside of the car as in motion because your reference point is in the car. If you are standing on the sidewalk, the objects like a tree would not be moving because you're standing still. So your reference point does make a big difference in how you describe something in motion. You will generally describe motions with reference terms like north, south, east, west, up, down, right, left, in a straight path, in a circle, around a track, something like that. So frame of reference, to give some idea of that is the object or point where movement is determined. So any object can appear to be in motion or at rest depending on your frame of reference. Motion is only determined when there is a frame of reference, and Earth is generally the most commonly used frame of reference because the Earth actually is in motion, but we are standing on Earth, so we don't talk about us being in motion. We then use ourselves or the Earth as our frame of reference. So relative motion is based on the person describing the motion, which is based on their frame of reference. So an example, when you're standing on the ground, that is your frame of reference. Anything you see, watch, or measure is compared to the reference point of you standing on the ground. Here's an example of what that would look like. The frame of reference for these two girls. The red dress girl uses the moving vehicle as her frame of reference, and to her, she is not moving. She would describe the yellow dress girl as moving because to her, the yellow dress girl looks as though she is moving. The yellow dress girl uses her frame of reference as a stationary position to see the red dress girl in motion. If we're looking at the skydivers here, we have a frame of reference for the skydivers. The plane is in motion away from them. Themselves are not in motion, and the ground is in motion towards them. So here's some examples. Sitting at your desk, how fast are you moving? Relative to the ground, 0. You are not moving. Relative to the sun, 2.97 times 10 to the 4th meters per second. So if there was an observer standing on the sun, although that would be odd, but if there was an observer standing on the sun, they would say you are moving at 2.97 times 10 to the 4th meters per second. However, when you base your frame of reference as the Earth, you are not moving at all. Example 2. While sitting at a red light, a bus stops in the lane next to you. As you're daydreaming, looking at the side of the bus, you all of a sudden feel like you're rolling backwards. At that point, you realize you look at some other object and you realize the bus is moving forwards when you take into account a stationary frame of reference. So this is what can confuse your brain, basically. And this is what can cause motion sickness. So you don't need to write this in, but just gives you kind of a tip of the day here. Motion sickness is caused by your brain getting the two different sets of information about your body's motion based on its frame of reference. So the information from your eyes and the information from your inner ear are mixed up, and that will cause that motion sickness. So to help with motion sickness, if you're one of those people that suffers from it, you try to look forward at a point far in the distance, which helps to give you a better reference, and you stay focused on that. So distance versus displacement. I'll give you kind of a comparison here. Distance is a scalar measurement, which means it's only an amount. You just give a number. Direction does not matter. The actual path does matter. The total distance traveled is important. So an example, in the Daytona 500, the cars travel a distance of 500 miles. Displacement is different in that it is a vector quantity, which is an amount and direction. Direction does matter. The path does not matter. And we are looking at a straight line distance and direction that the object has traveled from its starting point. So from point A to point B, we're looking at the straight line path, not all the roads or turning or different things that you might have to do to get there. In this case, the Daytona 500, the cars will experience zero displacement because they start where they end. So the point A and point B is the exact same spot, so they have zero displacement. They have ended up exactly where they started. Here's another example. What is the overall distance traveled in the picture below, and what is the overall displacement in the picture below? So if we were to look at leg 1, going from start here to leg 1, the distance traveled is 2 meters. The displacement from point A to point B at this point is also 2 meters because it's a straight line path. Leg 2 distance, if we go from start down this path to leg 1 and then we follow along to leg 2, we've got 6 meters. But displacement is going to be this straight line path. Now if you look at this will take you back a little bit to math. We're going to have to use the Pythagorean theorem to come up with this straight line because we've got a triangle. We're figuring out this line here. So that is a squared plus b squared is equal to c squared. Now again, you only do this if your straight line path is this and finishing off the triangle. So we've got 2 squared plus 4 squared is equal to c squared. So 2 squared is 4, plus 4 times 4, which is 16, is equal to c squared. 4 plus 16 is 20, equal to c squared. We then need to do the square root, which c is going to be equal to 4.5. So displacement at this point is 4.5 meters. The leg 3 distance, we go from leg 1, 2, plus 4, plus 2. So at this point we are at 8 meters that has been traveled in distance. And displacement from point A to point B is only 4 meters. You can see how they are different here. Our final distance then is going to be taking leg 4 into account. And so we have 8 plus 4. That's going to give us 12 meters. But our displacement is the start and the end are at the same place. So our displacement is actually 0 meters. If we were to look at this in a picture like on a map idea, then you can see what is happening here as well. If this is point A and this is point B, your distance traveled is going to be this entire distance. And so you're going to take 8.2 plus 1.8 plus 4.5 to get your total distance. However, displacement is the straight line path across from point A to point B, and so displacement is only 2.7 kilometers. Now notice also there is direction that's given to it. In this case, it is given an angle as a direction. Vector diagrams are when we show direction and motion with an arrow. So the size of the arrow will indicate relative speed of that object. So we would do this, you saw some of these on the displacement and distance graphs or charts. We can show this if a car is in motion. We can show in this one that the car is maintaining constant velocity because the arrow size never changes. And that is represented here as well, the same picture. If an object is accelerating, we might show the arrows increase in size to show that the object is increasing its speed or velocity, which is also changing or accelerating. It's changing the velocity. We will work more with vector diagrams as we get into forces and be able to show which force is stronger than another or if there are balanced forces. So we had a worksheet as a class at this point. If you need to check that or you need to work with this a little bit more, please let me know and we will either practice it more together or we will I'll give you some extra work that you can do to practice it.